Ouais, on a encore une fois du mal à t'entendre.
Marc, est-ce que tu peux
Excusez-moi.
ton gauche, ça siffle quand tu as ton micro. Super, c'est bon là, ça siffle plus.
Voilà, donc Sylvain, je disais que Sylvain travaillait à l'ILL après avoir aussi travaillé dans divers synchrotrons, je pense, et que tu es spécialiste de neutrons ou de rayons X aux petits angles pour l'étude de systèmes de la matière molle essentiellement. Je ne saurais pas dire où tu as fait ta thèse ou ce que tu as fait comme étude avant.
Ma thèse était à Saclay avec Thomas Zimb.
D'accord, ok. Et puis, aujourd'hui, tu vas nous parler d'auto-assemblage dans des liquides complexes?
Oui.
Si j'en crois à peu près le titre, non? C'est pas tout à fait ça?
À peu près. Je ne sais pas exactement comment ça va s'organiser, mais disons que je pense parler d'abord de petits angles et ensuite d'auto-organisation et notamment de microémulsion sans surfactant.
D'accord. Alors, est-ce que tu es d'accord pour faire le séminaire en anglais?
Oui, bien sûr.
Il y a plusieurs...
À tout détail, en général, je les enregistre pour que les étudiants puissent revenir dessus. Donc, si quelqu'un n'est pas d'accord, je ne le fais pas. Hein. Donc, c'est juste, voilà, s'il y a quelqu'un qui n'est pas d'accord, il le dit et puis je le enregistre. En général, je le mets en ligne pour que les étudiants puissent revenir dessus. Donc, le record de vue, pour l'instant, c'est 150 vues sur les record à mais si tu ne pas, il n'y a aucun problème.
Eh bien, écoute, Sylvain, je pense que tu peux commencer?
Oui. Alors, juste une chose, n'hésitez pas à m'interrompre et à me poser des questions pendant le séminaire. Hein.
Okay.
Aucun problème avec ça.
If you didn't understand in English, please interrupt Sylvain if you have questions during the seminar.
Okay, you can see my presentation.
Yes.
So, my name is Sylvain Prevost. I'm working at the Institut Laoué-Langevin in Grenoble. So I will briefly talk about large-scale facilities where I'm working, then small angle scattering, the technique I'm using, then again briefly self-assembly, and then I will focus on surfactant-free microemulsions, which is one of the topics I'm most concerned about since a couple of years. So first, where I work at the European Photon and Neutron campus on the other side of Grenoble compared to the university. I don't know if all of you had the chance to visit the EPN campus and to visit ESRF, the European Synchrotron, and ILL, the European Neutron Source. They are both large-scale facilities, so they have instruments that they make available for experiments by external users, scientists to apply for a given experiment on a given topic. So ESRF is the most brilliant X-ray source for research. It has 40 instruments, more or less 5,000 scientists a year, far less since last year, actually. And you probably all know, at least from outside, the large ring, storage ring of the synchrotron, which is almost 1 kilometer long. And next to it, and far less known, is a nuclear reactor. So lots of people in Grenoble do not know that. So that's the ILL, the European Neutron Source, which is the most powerful neutron source for research, which with also 40 instruments and call for experiments and more or less 2,000 scientific visitors per year. And what I do, I'm an instrument scientist. So I'm a scientist in charge of an instrument, which is a small angle neutron scattering instrument, D11. And so my job is to collaborate with scientists around the world who apply for beam time and do experiment at ILL. And I work mainly on self-assembly in soft matter, but I'm going towards more and more biologically relevant systems. So I do not know how familiar you are with small angle scattering. I have a few slides to tell you or remind you what it is. You send a coherent planar wave on a sample, and this wave will interact with the content of the sample. This interaction will result in spherical waves, and these spherical waves will interact destructively and constructively in the far field, creating interference patterns. And from this pattern, you will infer characteristics in your sample. So depending if the interferences are caused by scatterers far away, you will create interferences at small angle near the direct beam. And when interferences are caused by scatterers next to each other, you will create these destructive and constructive interferences at large angle far away from the direct beam. And when do you use small angle scattering? Well, small angle scattering helps you probe spatial correlations in your samples. So it tells you about shapes, dimensions, size distributions, and interactions in your material, which is nice, except that you get all this information together. So you get data that you need to interpret with models to extract useful information. Compared to other techniques, it uses quite large volumes. The advantage is that you have a statistical relevance of what comes out of the experiment. You get an ensemble average over a large volume of your system. Another big advantage is that you have no sample preparation needed, meaning also that you can look at your sample in situ or in operando. It means under external conditions like applying a mechanical stress, a thermal stress, a pressure, and so on. And you can use this technique with X-rays if you go to ESRF, so small angle X-ray scattering, SAX, and you have lab SAX available. And you can use these techniques with neutrons, that's small angle neutron scattering, SANS, if you go to ILL or other neutron sources. The landscape that you probe with small angle scattering is of the order of 1 to a few hundreds or thousands of nanometers. So it's above molecular size. It covers macromolecules and biomacromolecules.
Les rayons X, c'est des neutrons.
T'es vraiment hyper intelligente, ma chérie.
Enlève ton masque.
T'es vraiment hyper intelligente.
Je crois qu'il y a quelqu'un qui a son micro d'allumé.
Pardon, vas-y.
So yeah, it covers everything from large molecules to self-assembled systems such as micelles, microemulsions, and even mini emulsions. And the experimental setup is in fact very simple. You just need a source producing a beam that is directed at the sample. Most of the beam goes through the sample. Part of the beam is scattered at different angles. So you put a detector in the direction of the direct beam. You protect the detector of the direct beam with a beam stop, and you look at how the samples scatter in angular dependence. A roof approximation to know which size you are looking at as a function of angle is given here. So the distance is typically the wavelength divided by the scattering angle. And if you make a quick calculation for a relatively large size of 100 nanometer and a typical wavelength that we use, you see that we are looking at 0.2 degrees angle, which is why the name of the technique is small angle scattering. We look very close to the direct beam. So this is a schematics of one of the SACS beamline of ESRF. It's a 100-meter long beamline called ID2, which has a very high flux. It's used mostly for time-resolved experiments. And as typical for this kind of large-scale facilities, you have standard proposals application, so calls twice a year. And within 6 months after the call, you can make your experiment if you have been allocated beam time. With synchrotron SACS, your typical acquisition time is of the order of milliseconds. And this is D11, the instrument I'm responsible of at ILL. It has a similar size to ID2. It's more or less 100 meters long. And as for ESRF, there are proposal calls twice a year and 6 to 12 months delay between applying for beam time and getting beam time. Compared to X-rays, neutrons have far less flux. It's actually much more difficult to produce a lot of neutrons than X-rays and to have them with low divergence. So measurement times are longer, typically it's minutes. The big advantage of SANS over SACS is contrast variation. You can isotopically label your system to identify different portions of your system. And this isotopic variation works extremely well if you have hydrogen and you can deuterate part of your sample. I invite you to have a look someday at an animation showing how small angle neutron scattering works at this address. So when do people use small angle scattering? They use small angle scattering when they want to identify characteristic sizes and shapes in their system. You certainly know another technique to do that, which is cryo-EM. Cryo-EM is extremely powerful, and quite often we try to couple cryo-EM and small angle scattering. In cryo-EM, you see images of your system, so you don't need necessarily to interpret the data. But you do have biases, in particular due to sample preparation. And you cannot do in situ or in operando experiments. You also lose statistical average information in cryo-EM. If you think of a relatively dilute solution of micelles or proteins, and you look at a sample of 10 microliter by SACS, you already observe 300 trillions of these particles. So you get a statistically relevant information that you don't get with microscopy techniques. And a few slides to conclude about small angle scattering. So what scatters is heterogeneities. If your sample has no heterogeneities, no change of composition with distance, you will not get scattering. So in small angle scattering, as we cover, let's say 1 to 1000 nanometer, you need to have changes of material composition over this length scale. And scattering will correspond to spatial correlation between different area of your sample. And to simplify the analysis, we distinguish spatial correlation from within one particle, and that's called the form factor, and spatial correlations between different particles, and that's called the structure factor. And to simplify even further, if you imagine a sample as an assembly of identical scatterers, you can imagine it as being the scattering from a single scatterer and the scattering due to the relative position of all these scatterers. So form factor, structure factor. There are a number of cases where this does not work well. It's a simplification. And the general equation to understand your data is to have the intensity written as a number of particles per unit volume. So concentration, the higher the concentration, the more intensity. The square of the volume of your particle, the larger the particle, the more they scatter. A contrast, which is a difference of scattering length density. A form factor that represent characteristic of a single particle, and a structure factor that represent how particles are distributed in space. So this is a simulated scattering pattern that you would obtain for spheres. This is for cylinders. You can see that they have a lot in common, spheres and cylinders. And finally, disks. And these oscillations that you see here are due to constructive and destructive interferences. We can analyze the scattering from any kind of shape as long as it's mathematically tractable. So I used to work at ESRF on a SAX instrument. I'm now working at ILL on a SANS instrument. Both techniques have advantages and cons. X-ray is much more affordable, much easier to access. You get higher flux, you get higher statistics for your data, you get your data in shorter time. It has a problem that X-rays can damage samples, and that X-rays are just sensitive to electronic density, which can be very interesting in a system which is composed, for example, of organic parts and inorganic parts, because inorganic parts will typically have higher electronic densities than the organic one. There are other systems in soft matter purely composed of organic parts where you will not have sufficient contrast to understand your data. So neutrons are far more difficult to access. There are fewer sources, fewer instruments. They have also less flux, so you need longer times to acquire your data. You do not get radiation damage. A lot of materials that would fully absorb X-rays will not absorb at all neutrons, so you can easily measure with neutrons a very thick piece of metal. It's also used by by a large community because neutrons are sensitive to magnetism. But the most interesting part for soft matter and also for biological system is that neutrons are sensitive to isotopes. So let's imagine you work with water, the system in water. If you can replace light water by heavy water, so H2O by D2O, you create a contrast with hydrogenated components. And you are not obliged to replace entirely H2O by D2O. You can work at different H2O D2O ratios, and then you can highlight or mask different parts of your system separately and precisely.
The mass difference, or
Sorry, I didn't get the question.
is this due to the mass difference or something else?
No. It's a characteristic of nuclei. So neutrons interact with nuclei. And to this day, we are not able to simulate the scattering lengths of all nuclei and all isotopes theoretically. So to analyze our data, we use tabulated values coming from experimental measurements. So apparently the physics behind the scattering lengths of nuclei is just too complicated today. Does that answer your question?
Yes, okay.
So if you want more information on scattering, and in particular small angle scattering, I recommend these 3 books. The first one is very useful for people working in soft condensed matter. The second one is more generic and will also apply to hard materials. And the third one is theory, but clearly explained with all the mathematics and physics you need to understand it. Okay, molecular organization. So I mostly work on soft matter, and what characterizes soft matter is very soft interactions, meaning that the stability of your system is driven by a very delicate balance between opposite forces. These systems, the academic system we study are often in thermodynamical equilibrium. We have also a number of users that look at out of equilibrium systems, which are often very relevant for industry, because in fact, a lot of practical products are not at thermodynamical equilibrium. And soft matter systems, because they result from delicate balance between different forces, can change, they can react, they can adapt to application of external stresses. So it can be mixing components, it can be changing temperature, pressure, anything. A lot of systems, soft matter systems, are used tremendously every day by everybody, and are huge, have huge industrial applications. So of course it's a case of detergents, but also paints, creams, and so on. They are also used in oil extraction. I think the financial market for detergent for oil extraction is in the billion range per year. There are some more specific application of soft matter, such as ferrofluids, which were developed at NASA to drive combustible out in the absence of gravity in a space shuttle, and which are nowadays used in hard drives and loudspeakers. You have, of course, all screens, which are composed of soft matter. Pharmaceutics, you know that RNA vaccines, which are currently made by BioNTech and Moderna, are based on solid lipid nanoparticles, which are quite complex assemblies of oppositely charged lipids and RNA. And obviously, all living systems are soft matter. So I want to present you a few slides of things I've worked on self-assembly before going to the topic that I'm interested in right now. Do you have any questions so far, either on the technique or on, well, anything at all?
Sorry, can you hear me? Hello, can you hear me?
Yes. I don't know if it's my connection or yours, but it's not very stable.
I think it's fine, but anyway, at which point do you destroy your cell when you put it in X-ray or neutron?
At which point do you destroy your system?
You have very high flux now. Does any effect on your sample?
I'm sorry, I don't hear you very well. I think you're asking.
Can you put living cell in the very high flux?
So yeah, so it's a good question, and it really depends on the cells. On a synchrotron instrument, where you have a huge flux of X-rays of the order of 10 to the power 12 or more, you destroy bacteria in less than a second, I would say, typically. Different systems have extremely different resistance to X-rays. One of the problems with X-rays typically it can be due to oxygen in the sample. So sometimes you can, if you can remove oxygen and dissolved gas in your sample, you can make your sample more resistant. But yeah, in general, bacteria will not survive long, but their shape will not change. So they will not reproduce anymore, they will not duplicate, they will not move. except via Brownian motion. With neutrons, there is barely any radiation damage. Indirectly, you may form tritium out of deuterium in your sample if you expose it very, very long times. And that will create radiation that could damage a system, but this is never reported. It would really huge, a gigantic flux. So in general, you can think of small angle scattering as a non-destructive technique. But with X-rays, you just have to be careful, especially at synchrotron instruments.
Okay, thank you.
Okay, so before to go into the topic of surfactant-free microemulsion, I wanted to show you a few things I've done over the years with small angle scattering. One of them was working with a boron-based ion, which has this shape here. So it looks like a tic-tac, essentially, a small tic-tac, 0.6 nanometer by 1 nanometer. And we were surprised to discover that it actually forms micelles, vesicles, and lamellar phases. And this was observed by small angle neutron scattering and small angle X-ray scattering, in addition to dynamic light scattering. So this is still soft matter, but already with a bit weird compound. Another thing that was done with small angle scattering, both SANS and SACS, but mostly SACS, was to look at what happened when you mix different systems. Here it was 2 different surfactants. And you can mix them with what is called a stopper flow apparatus for rapid mixing to see what happens within milliseconds of mixing together self-assembled micelles that will interact together. And because of the high flux of synchrotron SACS, you can follow millisecond after millisecond what happened. A lot of systems in soft matter are extremely fast. So you get this kind of intensity profiles as a function of time. And by analyzing the data with analytical model, you understand what happened in terms of nanostructures. So you start with 2 different types of micelles. They mix together to form discs. The discs are growing, and beyond a certain size, they collapse to form closed vesicles. But analysis is a huge part of small angle scattering, and in fact of a lot of soft matter experiments. So what took time here was to understand theoretically what was happening and being able to reproduce with a set of equations exactly what was going on in the sample over time. This was done by something that you probably worked already in your courses, the Smolorowski set of equations, Smolorowski kernel. So it showed a growth by fusion of the disk until flexibility overcome the cost of the rim energy, so that it would close as vesicles. Just to stay in the realm of small angle scattering as a function of time, the technique, we also use a technique to look at the growth of nanoparticles induced by polymers. So it's still a soft matter system where polymer interaction with ions drives the nucleation of growth of a nanoparticle. And here the aim was to reproduce magnetic nanoparticles that you can find in a number of bacteria, which are magnetotactic. But to come to the topic of interest for today, I will talk to you about pastis or ouzo. So I guess you are all familiar with these kind of drinks, which are typical from the Mediterranean region. And what I want to show you is that the apparent simplicity in soft matter is rarely followed by simplicity of behavior. So you've probably all made yourself a pastis or ouzo, taking a bottle of concentrated alcohol solution and adding to it water and observing a turbidity appearing and getting stable for days. So this looks very trivial. In fact, it's not. And there are more and more articles about this kind of phenomenon where complex fluids are obtained without any macromolecule and without any surfactant. And this kind of phenomenon happens everywhere. I will show you a bit later a number of examples. But it happens also in industrial processes like in extraction of metals, in biological processes and so on. And the nanostructuration of this kind of fluid can explain a number of anomalies that were detected for a long time but were not really, or rather their origin was not understood. So, and this fluid, I will show that they actually behave like microemulsion. So they are called surfactant-free microemulsion and sometimes ultra-flexible microemulsion. So what is pastis? Pastis is essentially a mixture, a quite simple mixture of three components: water, ethanol, and anise oil, which gives a flavor to the drink. And when you buy a bottle of pastis, you buy something which has the composition written in the ternary here. I guess you are all familiar with ternary phase diagrams. So in a ternary phase diagram is a phase diagram for three components. In this corner, you have pure water. In this corner, you have pure ethanol. In this corner, you have pure anise oil. So when you buy a bottle of pastis, which has a composition written with a star here, what you buy is essentially 60% water, 40% ethanol, and traces amount of anise oil. And what you do when you make your pastis is that you add water. So you go from this composition to a composition closer to that of pure water. And by doing that, you cross a phase boundary and you enter a biphasic domain. So your turbid sample is in fact an emulsion with large droplets of oil in a water-rich phase, which is stable for hours typically. So this is a glass of the original drink, and this is a glass after you add water.
This reaction is reversible for the pastis.
What did you say?
Is it reversible for the pastis?
It's reversible with a hysteresis. So it would be reversible over a very long time. To make it reversible, you could add a huge amount of ethanol to your pastis.
But you say there is an hysteresis on that.
Yes, a very large hysteresis in temperature and in composition.
How do you explain this?
Actually, when you make your pastis, you cross more than the binodal, you cross the spinodal, and you enter quite deep into the biphasic domain immediately. Otherwise, you would not get the appearance of turbidity, so this milky aspect.
Okay, thank you very much.
On top of that, there is another hysteresis that we don't really understand well, which is probably mostly based on diffusion of compounds, but this is still under investigation. So we were interested in working on this type of fluid, so pastis-like fluids. And we were interested in two aspects. The first one is what is inside the original solution and what happens when you add water before it gets turbid. And the second is to what this turbidity corresponds. And this is a result of a collaboration with experiments performed at ILL and ESRF and a team working on it at CEA and in Germany, in Regensburg. So the first thing that we did was to do a lot of small angle X-ray scattering. So as I said, SACS acquisition takes milliseconds, so it's very easy to measure a large number of spectra. And we covered more or less the entire monophasic region of the phase diagram. So each of the points represented in these triangles correspond to a sample measured by SACS. The data are presented here. So those are the data intensities as a function of the wave vector Q. And you can see that they change a lot with composition anywhere in the phase diagram. And we managed to fit all these data with a very simple model. So I will not go into the details of the model, but it's interesting to note that we hesitated for a long time between different models until we finally found the right one. And we found the right one because we had many points everywhere in the phase diagram, and we were looking for a model that could explain all the data. Before that, other models were used because only few spectra in some corners of the phase diagrams had been measured. So I think it's important to keep in mind that most data, not just small angle scattering, most data, not just small angle scattering. Sorry. So most experimental data, not just small angle scattering, require analysis and must be confronted to hypotheses. And whenever you have a limited amount of data, you may do a wrong assumption on the analysis that you perform and on the hypothesis that you test. So many data are often useful to get the right idea about your system. Anyway, so whatever the type of scattering pattern that we observed, we were able to reproduce it with a model that correspond to the coexistence of two nanostructures in the system. And these two nanostructures are water-rich and oil-rich domain, as in any microemulsion. But contrary to the microemulsions that you know, which have a relatively well-defined shape and size, these resemble more critical fluctuations. So they are almost random domains in size and shape of water in oil or oil in water. And on top of that, we have a second level of structuration. So it's hierarchical because the oil-rich phase self-organizes due to polar moieties contained with the alcoholic groups, which are forming this kind of blue small mesh. To confirm that, we did quite extensively molecular dynamics, which is why it's very nice to have collaborations, because you cannot hope yourself to master very different techniques. So molecular dynamics simulations were performed in Regensburg. And here you see a snapshot from molecular dynamics, where only the octanol molecules have been are shown. Here only the water molecules are shown, and here ethanol molecules are shown with octanol, ethanol which is close to octanol, and here ethanol molecules close to water. So you can see that there is a weak structuration in the system. Again, it's not as well defined as microemulsions as you are used to, but definitely the molecules are not randomly distributed in space, which is why we see all these scattering patterns. So we compared molecular dynamics results with small angle scattering, and to be completely sure of what we were seeing and saying about our system, we measured samples at the same composition with different contrast using isotopic labeling and combining small angle neutron scattering and small angle X-ray scattering. So here's a combination of different small angle scattering techniques, and molecular dynamics helped us finally understand our system completely. Here I'm showing the experimental small angle scattering data with continuous curves and the molecular dynamics simulation with points to show you that they perfectly agree with each other. So molecular dynamics is very powerful, and you are probably getting some lessons on it. One problem for soft matter with molecular dynamics is still the limit in box size. It's quite hard to go beyond 10 nanometer box size, which is why here the simulation from molecular dynamics are stopping quite at quite high Q, meaning at quite small sizes. So you can have in mind that the molecular dynamic simulation range goes from atom to 10 nanometer, while the small angle scattering experiments are going from angstrom to hundreds of nanometer. So because small angle scattering can be used in situ or in operando, we actually watched what happens when you make pastis. So we did it with actual pastis and water, and that didn't work well. So we did it with a model system that I was talking about just now, of where we replace the anise oil with octanol. But the concept is the same. So we started with a solution of ethanol and an oil, here octanol, instead of anise oil. And we diluted continuously with water on the beamline, in the beam, to get the intensity profile as a function of the volume fraction of added water. And then data analysis allows us to extract a number of parameters from this system and to detect a number of domains that were not known before or not seen before. Domains of concentration fluctuation, which are fully random, and domains of what we call ultra-flexible microemulsion or surfactant-free microemulsion. And we complemented that again with small angle neutron scattering and theoretical simulation in addition to molecular dynamics. So theoretical simulation based on random size of domains. And this square illustrates the composition of the sample with, as before, the orange part representing oil-rich domains and the blue part representing water-rich domain. So we start with the usual ternary phase diagram. We start from the monophasic part where it's fully stable and clear. And then we go into the biphasic domain at different depths into the two-phase regime. So when we are monophasic, we have this random distribution of oil and water. Then when we add, when we just cross the biphasic domain, we start forming droplets. This is when the appearance of turbidity occurs. And this first step is very, very stable over time. And it corresponds, in fact, to a weak separation between droplets and the continuous medium. So you have oil-rich large droplets in a water-rich medium. But in fact, both phases are nanostructured, and the oil-rich domain contains a lot of water, and the water-rich domain contains still quite a lot of oil. which probably explains the resilience of these droplets to phase separation. And if we go deeper into the biphasic regime, we get a better and better separation between oil and water, and less and less stability. And if we go too deep into the biphasic regime, so this would correspond to diluting too much your pastis or ouzo drink, then we get almost pure oil in almost pure water, and this is really not stable at all. It means it phase separates within seconds. And of course, one puzzle was, why are these microemulsions stable without a surfactant? So you're familiar with standard microemulsion, where a film of surfactant separates oil and water and stabilize the oil domain in water. And stabilization typically occurs via steric forces and electrostatic forces. And you have neither of that in the case of these liquid mixtures of solvents, which have no surfactant. And you would expect that entropy would favor a full distribution, a random distribution of your molecules in the medium. And you would also expect that in case there would be domains of oil in water forming, they would immediately collapse due to attractive van der Waals forces. And in fact, what was obtained from theoretical analysis and from molecular dynamics is that hydration forces is what stabilizes those systems and gives them a characteristic size. But the characteristic size that is much more loose than the relatively well-defined size you obtain with surfactant in the case of microemulsion. So as we dubbed them microemulsion, the question would be, can they actually be used as microemulsion? And microemulsions, as you certainly know, are typically used to solubilize very hydrophobic compounds. So we took the most hydrophobic compounds we had in the lab, which was squalene, which is pharmaceutically and biologically relevant. And it's extremely hydrophobic. And we saw that indeed these microemulsions, so these apparently random fluctuations of domains of oil in water, can solubilize, can uptake fully hydrophobic compounds. So I talked about drinks, but in fact, it goes much beyond simple drinks. And this kind of nanostructurations, we are starting to observe it a bit everywhere. So we see that the type of ternary phase diagram where we find those nanostructurations are in fact very often used without really knowing why in a number of syntheses. It can be a synthesis of nanoparticles, such as silica nanoparticles. It can be a synthesis of polymer latexes or other syntheses of nanoparticles. There are also a number of systems for which we see quite often very similar data. So basically, as soon as you mix different molecules together, even if you think that what you get is a continuous, homogeneous, random solvent, most likely it isn't. And it can also explain a number of things that were known but not really understood. Even, for example, a simple question as how self-assembled systems are dissolved by alcohol. You may be familiar with the fact that foam, and in general micelles, will be destroyed by the addition of alcohol to your water solution. This is known, yes, but it's not really understood. The mechanism behind it is not really understood. So we believe it's a quite generic process, quite generic occurrence. This is a typical ternary phase diagram of many things you may have in your bathroom. So a lot of solutions are actually composed of water, ethanol, and some fragrance or some oil, which will have very low solubility in water. So it's the case for perfume, for eau de cologne, aftershave, and so on. And there is, in fact, a more and more vast body of literature on these kind of system. Just they have a lot of different names in different disciplines. So you need to look at a large number of keywords to find out all the literature relevant for this kind of system with very weak nanoscale organization. So in soft matter, it will be typically surfactant-free microemulsion or detergentless microemulsion. But you will also see in chemistry solution structure. You will read sometimes about open micelles or solvent network. So we believe they already have a number of applications, just we don't know about them. And one of our collaborators in Regensburg actually used that to make a very good solvent for city walls against graffiti. Do you say graffiti in English, actually? I'm not sure. And the system is of outstanding interest to study weak forces. You will see in your studies a number of data on relatively strong forces interactions in soft matter, especially electrostatic and van der Waals. But there are also other forces which are much weaker and which are less well understood and therefore used and harvested. So the conclusion. So I hope I managed to convey the fact that systems that look simple and that everybody knows may still lead to interesting discovery when you look deep enough. And there is always a chance that you don't realize that, because typically in research, you only find what you are looking for. If you are not looking for an information, you will not find it. There are fluctuations in matter that was often considered to be quite homogeneous, and this seems to be quite systematic. It has a number of fundamental importance. In chemistry, in biochemistry, it is believed that a number of catalytic effects are due to these. In thermodynamics, to understand nonlinearity effect. And there is a lot to learn about these in terms of dynamics in particular. I hope I could also convince you that small angle scattering is an interesting method. And of course, if you have any question on small angle scattering, you can write me at any time to me or my colleagues. In general, if you are interested in a technique available at a large-scale facility, you should never hesitate to contact instrument responsible, who are more than happy to help you understand